Somewhere above you, about 10 billion light years away, there is a structure so wide that it should be physically impossible. A wall of galaxies stretching nearly 10 billion light years across. Our entire observable universe is only 93 billion light years wide. This thing takes up a tenth of it. We will visit the structure that breaks the universe's rulebook, the empty void warping the temperature of space, and the ring no one can explain. If you enjoy the journey, subscribe. You won't want to miss what's coming. Now brace yourself. We begin. Sometime in the early 2000s, a team of astronomers was doing something that sounds almost boring. They were plotting dots on a map. Each dot represented a gamma-ray burst, the most violent explosion the universe produces. They weren't looking for anything revolutionary. They were cataloging, organizing, just doing the work. Then someone stepped back and looked at the whole map. The dots weren't scattered randomly. They were clumping, clustering together in one region of the sky in a way that made the room go quiet. A concentration of gamma-ray bursts, so dense, so wide, so geometrically absurd that the first instinct was to assume a mistake. Check the data. Run it again. Look for the error. There was no error. What they were seeing was the outline of something so large that modern cosmology had no framework to contain it. A structure built from thousands of galaxies, stretching across a region of space so vast that the human mind genuinely struggles to process it. Scientists would later calculate its width at nearly 10 billion light years. To put that in perspective, if you shrank the entire Milky Way galaxy down to the size of a single grain of sand, this structure would still be wider than the entire United States. That comparison doesn't fully land until you sit with it. The Milky Way holds somewhere between 200 billion and 400 billion stars. It takes light 100,000 years to cross it. And in this analogy, that entire galaxy, all of it, is one grain of sand. The structure we are talking about spans a beach. This was the first glimpse of what scientists would call the Hercules Corona Borealis Great Wall. Named after the constellations in the direction we see it, the structure sits roughly 10 billion light years away, meaning the light reaching us from it left before our sun even existed. We are looking at something ancient, enormous, and deeply inconvenient for the people whose job it is to explain the universe. The inconvenience isn't cosmetic. The existence of a structure this large doesn't just challenge one theory or tweak one equation. It cuts directly at the foundation of modern cosmology, a principle so fundamental that every major model of the universe is built on top of it. A principle most scientists had assumed was simply true, the way you assume the floor will hold your weight. That principle has a name, and once you understand what it claims, the existence of this structure stops feeling like an interesting anomaly and starts feeling like a warning. The data was reviewed, checked, cross-referenced. Other teams looked at it. The clustering held up. The structure was real. And across the cosmology community, a quiet, uncomfortable conversation began. If this thing exists, and it does, then something in our understanding of the universe is seriously wrong. Astronomers didn't announce a crisis that week. Science moves carefully, but behind the careful language and the peer-reviewed papers, the implication was loud. The universe had just shown us something it wasn't supposed to be capable of producing. And this was only the first surprise. The deeper you go into what this structure means, the stranger it gets. Because the problem isn't just the size, the problem is the time. The universe is only a certain age, and structures don't grow overnight. They grow slowly, pulled together by gravity over billions of years. So when you find something this big, the first question isn't just how. The first question is when. And the answer to that question is what keeps cosmologists awake. Something built. This. And whatever it was, it worked faster than the laws of physics say anything should. Every model of the universe starts with an assumption. One single idea so foundational that without it, modern cosmology doesn't function. It's called the cosmological principle, and for most of the 20th century, scientists treated it less like a hypothesis and more like a fact of life. The idea is simple on the surface. At large enough scales, the universe looks the same in every direction. Zoom out far enough, and matter is spread evenly, smoothly, with no special regions and no extreme clumping. Every patch of sky, if you look at it from far enough away, should be roughly equivalent to every other patch. The universe has no center, no edge, no favorite direction. This principle isn't just philosophical tidiness, it's load-bearing. Remove it, and the equations that describe cosmic expansion stop working cleanly. The models that predict how galaxies form, how dark energy behaves, how the universe evolved from a hot, dense plasma to the structured cosmos we see today, all of those depend on the cosmological principle holding at the largest scales. Scientists didn't pull this idea from nowhere. Early observations supported it. When you map the distribution of galaxies across the sky, things do look roughly even from a distance. The cosmic microwave background radiation, the faint afterglow of the Big Bang still detectable today, appears nearly uniform in every direction, varying by only tiny fractions of a degree. That uniformity became one of the strongest arguments that the cosmological principle was correct. The principle also has a philosophical appeal. It removes humanity from a special place in the universe. We're not at the center. Our region isn't unique. Every observer, no matter where they sit in the cosmos, would see roughly the same large-scale structure. It's an elegant idea, humble even. But elegant ideas have been wrong before. The universe does have structure. Stars form galaxies. Galaxies form groups. Groups form clusters. Clusters connect into long filaments stretching hundreds of millions of light years, like the threads of a cosmic web. Scientists always knew this smaller scale structure existed, and the cosmological principle didn't deny it. The claim was always that above a certain scale, above a threshold scientists estimated at roughly 300 million light years, the structure averages out. Everything smooths. The foam becomes a flat surface. That threshold matters. Scientists call it the homogeneity scale. Below it, clumping is expected and normal. Above it, the universe should look uniform. This is where the cosmological principle makes its stand. And for decades, observations were consistent enough that the principle survived unchallenged. Then structures started appearing above that threshold. Structures that crossed 500 million light years, then a billion, then several billion. Each discovery was debated, questioned, and often dismissed as a statistical artifact or a projection effect. But the discoveries kept coming. And the Hercules Corona Borealis Great Wall sits at nearly 10 billion light years across, which is roughly 30 times larger than the homogeneity scale the cosmological principle requires. 30 times, not slightly over the line, 30 times past it. The cosmological principle doesn't bend for 30 times. It breaks. And scientists know this. Many have said it plainly in their papers. A structure this large, if confirmed to full confidence, means the principle is wrong at some scale, which means the models built on top of it are incomplete, which means everything we think we know about how the universe is organized needs to be rebuilt around a new foundation. The question is, what does that new foundation look like? Nobody has a clean answer yet, but the search for one is leading researchers somewhere deeply strange, and the first step toward understanding it is asking how any structure this enormous ever got built in the first place. Gravity is patient. Enormously, almost incomprehensibly patient, and the large-scale structure of the universe is its greatest masterpiece, built over billions of years through nothing more dramatic than matter slowly pulling on matter. Here's how it works. After the Big Bang, the universe was nearly uniform. Nearly, but not perfectly. Tiny fluctuations in density existed, regions where matter was fractionally more concentrated than the surrounding average. Those regions had slightly stronger gravity. They pulled in more matter. That extra matter increased the gravity further, attracting even more. Over hundreds of millions of years, these small advantages compounded. Gas collapsed into the first stars. Stars gathered into galaxies. Gravity kept working, connecting galaxies into groups, groups into clusters, and clusters into the long filaments and massive walls that make up the cosmic web. This process has a speed limit built into it. Gravity can only pull matter at the rate gravity allows. And the universe, while old by human standards, is not infinitely old. Cosmologists have measured its age at roughly 13.8 billion years. That number is the hard ceiling on how long gravity has had to work. Picture it like a construction project. You have a crew, a set of tools, and a fixed window of time. The final building can only be as large as the time and tools allow. You can't build a skyscraper in an afternoon, and the universe can't build a 10 billion light-year structure in 13 billion years, at least according to the standard model. Scientists can calculate how large a structure gravity should realistically be able to assemble given the universe's age and the speed at which matter moves. That maximum comes out to somewhere around 1.2 billion light-years across for the largest coherent structure. That's the theoretical ceiling, with generous assumptions. The Hercules Corona Borealis Great Wall is nearly 10 times bigger than that ceiling. Now, gravity doesn't work alone. Dark matter plays a major role. Dark matter is a substance that doesn't emit or absorb light, so we can't see it directly. Scientists confirmed it exists through its gravitational effects on galaxies, on light bending around galaxy clusters, and on the large-scale structure of the cosmic web. Dark matter outweighs regular matter by roughly 5 to 1 across the universe. It was the invisible scaffolding that allowed the cosmic web to form as quickly as it did. Dark matter helps a lot. It accelerated structure formation significantly. Without it, galaxies wouldn't have formed as early as they did, and the cosmic web would look far more diffuse. Dark matter made the timeline work for ordinary structures. For the Hercules Corona Borealis Great Wall, even dark matter falls short. Physicists have run the simulations. They've modeled universe after universe inside supercomputers, adjusting dark matter densities, tweaking the initial conditions, giving gravity every advantage the math allows. The structures that emerge in those simulations reach enormous sizes, but they don't reach 10 billion light-years. The number simply doesn't come out. Something else is needed to explain what we're seeing. Either the structure formed under conditions very different from what the standard model describes, or the universe had more time than we think, or the initial density fluctuations after the Big Bang were far more extreme than current theory predicts. Each of those options carries heavy consequences. Each one requires revising something fundamental. And here's the part that makes this genuinely unsettling. This structure wasn't found by building a telescope pointed directly at it. It was found by accident, hidden inside data nobody expected to tell this particular story. Nobody set out to find the largest structure in the observable universe. The data that revealed it was collected for a completely different reason. And that might be the most unsettling part of the whole story. Gamma-ray bursts are the brightest explosions in the universe. A single burst, lasting anywhere from a fraction of a second to several minutes, can briefly outshine an entire galaxy containing hundreds of billions of stars. They're produced when massive stars collapse into neutron stars or black holes, or when two neutron stars violently merge. For a few seconds or minutes, they release more energy than the sun will produce across its entire 10 billion year lifetime. Because gamma-ray bursts are so luminous, they can be detected across enormous distances. We can spot them from billions of light years away. That extreme visibility makes them useful as cosmic markers. If you know roughly how energetic a burst is, you can use its observed brightness to estimate its distance. Plot enough of them across the sky, and you start building a three-dimensional map of the universe at very large scales. A team of astronomers used gamma-ray burst data catalogued over years of observations to do exactly that. Their goal was to understand the distribution of these bursts and what it might say about the regions of space where massive stars were dying. The analysis was statistical, careful, and not particularly headline-grabbing in its original design. But the map they produced showed something the team wasn't looking for. In a specific region of the sky, toward the constellations Hercules and Corona Borealis, gamma-ray bursts were clustering far more tightly than chance would predict. The probability of that clustering being random noise was calculated at less than 0.5%. Statistically, the clustering was real. The team traced the outline of the region where the bursts concentrated. When they measured it, the result was staggering. The structure they had inadvertently mapped spanned roughly 10 billion light years. A wall of galaxies so enormous that it had gone unnoticed because no previous survey had been designed to look at scales that large. The paper was published in 2015. The scientific community's response was cautious, as it should be. Gamma-ray burst mapping carries uncertainties. The sample size, while large enough to be statistically meaningful, still has limitations. Some astronomers argued the clustering could reflect observational biases rather than true physical structure. Those are fair concerns. Science demands scrutiny, and the Hercules Corona Borealis Great Wall has not yet been confirmed to the same confidence level as smaller, more thoroughly mapped structures. Researchers classify its status as a strong candidate, with ongoing analysis still being conducted. But here is what makes the discovery hard to dismiss. When independent teams reanalyzed the same data, using different statistical methods, the clustering held up. When additional gamma-ray burst data was incorporated, the signal remained. The structure's outline didn't dissolve under pressure. It persisted. And something else persisted too. A growing list of other structures, found through entirely different methods, also sitting at scales where the cosmological principle says nothing should be clustering. The Hercules Corona Borealis Great Wall was the most extreme. But it wasn't alone. The universe seemed to be accumulating a file of violations. One anomaly can be dismissed, two can be coincidence. But as the list grew, the coincidence explanation began to lose traction. Something strange was clearly happening at the very largest scales. And what came next would make the Hercules Corona Borealis Great Wall look almost familiar. There is a clock built into the universe, and it sets a hard limit on how big anything can get. To understand why the Hercules Corona Borealis Great Wall is so problematic, you need to understand what cosmologists call the particle horizon. It's a boundary, a wall of a different kind. The particle horizon marks the maximum distance from which light or any signal could have reached us since the beginning of the universe. The universe is roughly 13.8 billion years old. Light travels at about 186,000 miles per second, the fastest anything in physics can move. So the farthest distance from which any information could have reached us since the Big Bang is roughly 46 billion light years. That's the particle horizon, the edge of our observable universe. Now apply this idea to structure formation. For a structure to become coherent, meaning for its parts to be physically connected and influenced by each other, those parts need to have been in causal contact. They need to have had enough time to send signals back and forth, to exert gravitational influence on each other, to coordinate their collapse into a single bound system. Two regions of space can only influence each other if they are within each other's particle horizon at the time the structure was forming. If they are too far apart, gravity from one side simply cannot reach the other side fast enough to pull it into the same structure. This is why the size of the largest structures in the universe has a theoretical maximum. It's not a suggestion from the models, it's a consequence of the speed of light and the age of the universe. Structure formation is fundamentally limited by how fast causal influence can travel. The maximum size for a causally connected structure under the standard model of cosmology lands at roughly 1.2 billion light-years. Some generous models push that up slightly, but the number doesn't move dramatically under any realistic set of assumptions. 10 billion light-years is nearly 10 times beyond that boundary. For regions on opposite ends of the Hercules Corona Borealis Great Wall to have gravitationally influenced each other, signals traveling at the speed of light would have needed to cross the structure multiple times over the age of the universe. The maths simply doesn't close. One proposed way out of this problem involves inflation. Cosmic inflation is the theory that in the first tiny fraction of a second after the Big Bang, the universe expanded at a rate far exceeding the speed of light. Regions that were once close and therefore causally connected got stretched to enormous separations almost instantly. This could, in principle, mean that regions now separated by vast distances share a common physical origin from before inflation occurred. Inflation is real. Scientists have strong evidence for it from the uniformity of the cosmic microwave background. But even under inflationary models, the structures that can form after inflation are still constrained by the post-inflation speed of causal communication. Inflation set the initial conditions. It didn't give gravity a shortcut. The Hercules Corona Borealis Great Wall, under current physics, had no mechanism to self-organize. The causal contact required to build it never existed, at least not in the universe we think we live in, which raises an uncomfortable possibility. Maybe we don't fully understand the universe we live in. Maybe the laws we're applying were calibrated on smaller scales and simply break down when you push out far enough. Or maybe something happened before the Big Bang that left fingerprints on the largest scales of the cosmos. That last idea is far stranger than it sounds, and it gets stranger the deeper you go. You can't see it. You can't touch it. Every attempt to detect it directly has failed, and yet without it, the universe as we know it would be unrecognizable. Galaxies wouldn't have formed on time. The cosmic web wouldn't exist. And structures like the Hercules Corona Borealis Great Wall would be even harder to explain than they already are. Dark matter is the hidden architecture of the cosmos. Scientists estimate it makes up roughly 27% of everything in the universe, compared to just 5% for the ordinary matter that makes up stars, planets, gas, and you. The rest is dark energy, a topic for another chapter. But dark matter's role in structure formation is impossible to overstate. Here's the problem dark matter solves. In the early universe, the ordinary matter, meaning protons, electrons, and atoms, was locked in a hot plasma that was constantly being pushed outward by radiation pressure. This radiation pressure prevented ordinary matter from clumping until the universe cooled enough for atoms to form, an event called recombination that happened roughly 380,000 years after the Big Bang. 380,000 years sounds like a long time. On cosmic scales, it's a heartbeat, and it means ordinary matter had a late start in the structure-building race. Dark matter doesn't interact with radiation. It doesn't feel radiation pressure. So while ordinary matter was stuck in that hot plasma, dark matter was already clumping. It was already building gravitational wells, invisible basins of concentrated mass, scattered across the early universe. By the time ordinary matter was finally free to move, dark matter had already sketched out the blueprint of the cosmic web. Ordinary matter fell into those pre-existing dark matter wells like water filling grooves in rock. The grooves were already there, carved by invisible hands. Matter just followed the map. This head start is why galaxies formed as quickly as they did. Without dark matter's early work, the universe's timeline for structure formation would be dramatically extended. The first galaxies might have appeared billions of years later. The cosmic web might look far thinner and more diffuse. Simulations that remove dark matter produce universes that look almost nothing like the one we observe. So when cosmologists try to explain the Hercules Corona Borealis Great Wall, dark matter is their first tool. Could an unusually dense concentration of dark matter in that region have accelerated structure growth enough to produce something this large? The honest answer is, researchers have tested it, and the numbers fall short. Even with generous amounts of dark matter seeded in that region from the beginning, the simulations don't produce a 10 billion light-year coherent structure within the universe's lifetime. The head start dark matter provides is real and powerful, but it has its own speed limits. It still requires time to accumulate, collapse, and pull ordinary matter along with it. Dark matter amplifies gravity. It doesn't break it. So the structure stands as a genuine challenge to the standard model, even after dark matter is fully accounted for. Something beyond the known ingredients seems to be required, and scientists have begun looking at possibilities that would have seemed extreme just 20 years ago. One of those possibilities involves the universe's initial conditions being far more extreme than current theory predicts. Another involves a force that behaves differently than gravity at cosmic scales. Both of those options lead somewhere deeply unfamiliar. But before we go there, it's worth appreciating just how thoroughly this structure defies our expectations, using the most visceral comparison cosmologists have come up with. Numbers at cosmic scales tend to slide off the brain. Billions of light years, trillions of stars. The figures are real, but they don't land emotionally. So cosmologists have developed comparisons designed to make the scale of the Hercules Corona Borealis Great Wall something closer to felt rather than merely known. Start with the Milky Way. Our home galaxy spans roughly 100,000 light-years across. It contains somewhere between 200 billion and 400 billion stars. It is, by any human measure, incomprehensibly vast. Astronauts and physicists alike have described looking at images of the Milky Way and feeling genuinely dizzy at the scale. Now shrink the Milky Way to the size of a single grain of sand, not a pebble. A grain of sand small enough to balance on the tip of a fingernail. At that scale, the distance from Earth to our nearest major galactic neighbor, the Andromeda Galaxy, would be about 2 inches. A comfortable arm's length away from your grain of sand sits another grain, the Virgo cluster, a dense collection of more than 1,000 galaxies that our local group orbits around, would be roughly the size of a football at that scale, big enough to kick, still manageable to picture. The observable universe, all 93 billion light-years of it, would span about 6 miles at this scale. 6 miles of space, and your grain of sand sits somewhere inside it. Now look for the Hercules Corona Borealis Great Wall inside those 6 miles. It would stretch for nearly half a mile end to end, a single structure, half a mile long, built from millions of galaxies each the size of a grain of sand, sitting inside a 6-mile universe. That's the scale we're dealing with, and the cosmological principle says that at scales above about 200 feet, in this analogy, things should average out and look smooth. The Hercules Corona Borealis Great Wall is nearly 13 times longer than that smoothness threshold. It dominates the map. It's impossible to average away. What makes this even harder to sit with is the time dimension. The light we detect from this structure left 10 billion years ago. Our sun hadn't formed yet. Earth didn't exist. The atoms that make up your body were scattered across different stars that hadn't even ignited, and that light, traveling at the fastest speed physics permits, has been crossing space ever since, just to arrive at our telescopes and tell us this thing is out there. The structure isn't just enormous, it's ancient. and its age compounds the problem. If it formed early in the universe's history, when the cosmos was younger and denser, the timeline gets even tighter. The universe had less time to build it, and less spread out matter to work with. Cosmologists have a phrase for structures that push the limits of what current physics can explain. They call them anomalies. The word sounds mild, clinical, but in science, an anomaly at this scale is a crack in the foundation, and the Hercules Corona Borealis Great Wall is turning out to share that foundation crack with a growing number of other massive discoveries. Some of them found recently, some of them found in ways that seem almost too strange to be coincidence. The next one was found hiding in a pattern of light, stretching halfway across the sky. The Hercules Corona Borealis Great Wall is the largest known structure in the observable universe, but it isn't alone in breaking the rules. Scattered across the sky, astronomers have been accumulating a collection of structures that each, independently, challenge the cosmological principle, and the list has been growing faster in recent years than most scientists anticipated. The first major offender was the Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey, one of the most comprehensive mapping projects in astronomy's history. The Sloan Great Wall spans roughly 1.4 billion light-years and sits about 1 billion light-years away. When it was discovered, it was the largest known structure in the universe. Scientists debated it intensely. Some argued it was a genuine coherent structure. Others suggested it might be a visual artifact of the mapping process. That debate took years to settle. The Sloan Great Wall was eventually accepted as a real large-scale structure, and at 1.4 billion light-years, it already sat above the homogeneity threshold the cosmological principle requires. Already, the principle was under strain. Then, larger structures kept appearing. The huge Large Quasar Group, found in 2013, stretched across roughly 4 billion light-years. Quasars are extremely luminous cores of ancient galaxies powered by massive black holes. Scientists used a cluster of them, 73 quasars spread across a region of the sky, as traces of the underlying matter distribution. The structure they outlined was enormous. Its discoverers stated directly that its existence was in apparent conflict with the cosmological principle. Then came the South Pole Wall, identified in 2020. This structure sits much closer to us, only about 300 million light-years away, but it stretches across a region about 1.4 billion light-years wide. Closer to home, and still above the smoothness threshold, each discovery arrived with its own debate, its own uncertainties, its own challenges to standard cosmology. Scientists remained careful. Single anomalies can be dismissed. Observational biases can create phantom structures. The history of astronomy includes several objects that seemed impossible until better data revealed a simpler explanation. But the accumulation is becoming difficult to attribute to bias or coincidence. Multiple independent teams, using different methods and different types of cosmic tracers, galaxies, quasars, gamma-ray bursts, are all finding structure at scales where the cosmological principle predicts only smooth uniformity. The anomalies aren't clustered in one survey or one methodology. They're showing up everywhere scientists look carefully enough. There's a word for when a theory keeps requiring exceptions. Scientists call it strain. The cosmological principle is under serious strain, and two recent discoveries, found just months apart, turned that strain into something closer to a full structural crack. One of them was a ring, a perfect ring of galaxies nearly 1.3 billion light-years in diameter, discovered in 2023, sitting so symmetrically in the sky that researchers initially wondered if their instruments were malfunctioning. The other was an arc, a curved filament of galaxies stretching across 3.3 billion light-years of sky, discovered just before the ring. also in 2023. Both sit well above the homogeneity threshold. Both are real, and both defy every standard model prediction for what should exist at their scales. The ring especially raised eyebrows, because a perfect ring at that scale suggests a different kind of physics than simple gravitational collapse. Something else may have shaped it. What that something else might be is where the story takes a genuinely unsettling turn. 2023 was a difficult year for the cosmological principle. Within months of each other, two separate teams announced two separate megastructures, both discovered in the same region of the sky, both existing at distances where the universe was supposed to look smooth. Together, they didn't just challenge the standard model, they forced a reckoning. The giant arc was discovered first. A team led by astronomer Alexia Lopez identified it while mapping the distribution of galaxies and galaxy clusters using their light signatures. The arc stretches across roughly 3.3 billion light-years of sky, curving gently like the edge of something far larger. It sits about 9.2 billion light-years from Earth, meaning the light reaching us from it left when the universe was less than half its current age. Lopez described the discovery as initially disorienting. The team checked and rechecked. They ran statistical tests to determine the probability of this arc appearing by chance in a universe governed by the cosmological principle. The result came back at less than 1 in 50,000. Statistically, this structure is real. The giant arc sits roughly at the boundary between explainable and not. Its size strains the cosmological principle significantly. Scientists have proposed that it might be a section of a spherical shell, an enormous bubble-like structure left over from early cosmic history. That explanation, if correct, would at least provide a mechanism. Baryon acoustic oscillations, the pressure waves that rippled through the early universe in the first 300,000 years after the Big Bang, leave spherical imprints in the distribution of matter. These are real, confirmed, and detected. They produce structures up to roughly 1 billion light-years across. The giant arc is more than 3 times larger than the biggest baryon acoustic oscillation structure. The spherical shell explanation requires either an unusual stacking of these waves or something beyond what standard baryon acoustic physics predicts. Then Lopez's team kept mapping, and they found the ring. The big ring sits just 2 degrees away from the giant arc in the sky, at almost the same distance. Nearly 1.3 billion light-years in diameter, it appears almost perfectly circular. A ring of galaxies drawn in space with geometric precision that seems almost deliberate. The statistical probability of 2 structures this large appearing in the same region of sky by chance was calculated to be extraordinarily low. Lopez and her team considered whether the 2 structures might be physically related, whether they form part of the same enormous system. Perhaps the cross-section of a single cosmic bubble seen at 2 different orientations. If that's true, the underlying structure containing both of them would be vastly larger than either one alone. Neither structure fits comfortably into any current model. Baryon acoustic oscillations can't produce them at their observed sizes without significant modification to the standard theory. Cosmic strings, hypothetical defects in the fabric of space-time left over from the early universe, have been proposed as a possible explanation. Cosmic strings are theoretical. Confirmed evidence for them hasn't been found, but their predicted signatures match the kind of large-scale geometric structures we're seeing. The simultaneous discovery of the giant arc and the big ring in the same patch of sky was the moment many cosmologists stopped calling this a collection of anomalies and started asking whether the standard model of cosmology is structurally incomplete. That question, once asked openly in published research, doesn't go away. And the 2 researchers who asked it loudest also pointed out something that made the situation even harder to ignore. These discoveries weren't made using some exotic new instrument. They were found in existing survey data, which means other structures like them might already be hiding in the data we already have. For decades, the cosmological principle operated as background assumption, the kind of idea so foundational that questioning it felt almost philosophical rather than scientific. It was the ground under the ground, the thing you stood on while you did the real work. That changed quietly, then suddenly. A growing number of cosmologists have now published papers directly challenging whether the cosmological principle holds at the scales where we're finding these megastructures. And the language in those papers has shifted from cautious hedging to explicit concern. The principle makes a testable prediction. Above a certain scale, the universe should be homogeneous and isotropic, meaning it looks the same in all directions and has no preferred regions. The scale at which this smoothness is supposed to kick in has been calculated at roughly 300 million light-years. Some estimates are slightly higher, some slightly lower, but the range is well defined. Every structure we've discussed so far sits dramatically above that threshold. The Sloan Great Wall at 1.4 billion light-years, the huge large quasar group at 4 billion, the giant arc at 3.3 billion, the Big Ring at 1.3 billion in diameter, the Hercules Corona Borealis Great Wall at close to 10 billion. Each one a direct observational challenge to the principle's predictions. A team of researchers formally tested this in a 2022 study by analyzing the distribution of galaxy clusters across a large portion of the sky. They found that the universe's matter distribution remains statistically anisotropic, meaning it looks different in different directions, at scales far larger than the homogeneity threshold. The results suggested the universe hasn't reached the smooth, uniform state the cosmological principle requires, possibly at any scale we can currently measure. Other studies have examined the alignment of quasar axes across vast distances. Quasars are oriented seemingly at random in small regions, which is expected. But at scales of billions of light-years, their rotation axes appear to align, which is precisely the kind of large-scale coherence the cosmological principle forbids. Then there's the so-called bulk flow problem. Large groups of galaxies appear to be moving in the same direction at velocities higher than the standard model predicts. This bulk flow extends across scales of hundreds of millions to over 1 billion light-years. The standard model attributes galaxy motion at large scales to local gravitational influences that should average out. The bulk flow suggests something is pulling on the universe in a preferred direction across enormous distances. Each of these lines of evidence was debated individually and could be explained away individually. A single anomaly in one data set is manageable. But when independent probes of completely different physical phenomena, structure size, quasar alignment, galaxy bulk flows, all point toward the same conclusion, the probability that they're all coincidental measurement artifacts drops towards something negligible. A number of cosmologists have now stated publicly that the cosmological principle should be treated as a working hypothesis requiring active confirmation rather than a settled foundation. Some have gone further. Astrophysicist Subir Sarkar at Oxford has argued that current data already provides sufficient grounds to reject the principle at large scales. That's a significant statement from a serious scientist. Rejecting the cosmological principle doesn't just tweak the equations. It removes the flaw from under modern cosmology and requires a complete rethinking of how the large-scale universe operates. The scientific community isn't there unanimously yet. Debate continues, but the burden of proof has shifted. The cosmological principle is no longer assumed. It's being tested. And so far, the universe keeps failing the test. What replaces it, if it falls completely, leads to territory that most physicists would have called fringe science just 20 years ago. A principle as foundational as the cosmological principle doesn't get replaced with a shrug. If the universe turns out to be genuinely inhomogeneous at the largest scales, meaning it really does have preferred directions, uneven matter distribution, and mega structures that exceed every theoretical limit, then the ripple effects through physics and cosmology are enormous. Start with dark energy. The accelerating expansion of the universe, the observation that galaxies are flying apart from each other at an increasing rate, is currently attributed to dark energy. Dark energy is described as a constant, uniform pressure filling all of space equally, pushing everything outward at the same rate in every direction. This description depends fundamentally on the universe being homogeneous at large scales. A uniform force makes sense in a uniform universe. If the universe is inhomogeneous, if it has large-scale structure that violates the cosmological principle, then dark energy's apparent uniformity might be an illusion. What we're measuring as a smooth cosmic acceleration might actually be the averaged result of complex, direction-dependent dynamics that only looks uniform because our sample size is limited. This matters enormously because dark energy is currently one of the biggest unsolved problems in physics. Its nature is unknown, its origin is unexplained, and if its apparent uniformity is a statistical artifact of our position and observational limits, then every model built on treating it as a constant is pointing in the wrong direction. Now consider cosmic expansion itself. The Hubble constant is the measurement of how fast the universe is expanding. In recent years, scientists have discovered something deeply troubling. When you measure the Hubble constant using early universe data, the cosmic microwave background, you get one value. When you measure it using late universe observations, nearby supernovae and galaxy distances, you get a different value. The two numbers don't match. This discrepancy is called the Hubble tension, and it's one of the most actively debated problems in modern cosmology. One proposed explanation for the Hubble tension involves large-scale inhomogeneity. If we happen to live inside a region of space that is slightly less dense than the cosmic average, something called a local void, then our local measurements of expansion would be faster than the true global average. The mismatch between early and late universe measurements could be a symptom of our position within an uneven universe rather than a flaw in our theories. If that explanation is correct, it means the cosmological principle's failure is directly affecting our most fundamental measurements of how the universe behaves. The consequences reach even further. The standard model of cosmology, known as lambda CDM, uses specific assumptions about large-scale homogeneity to simplify the equations governing cosmic evolution. Those simplifications aren't arbitrary. They make the mathematics tractable. Remove the simplifications, and you need a far more complex framework that accounts for large-scale variation at every scale. Nobody has built that framework yet. The mathematics required would be genuinely formidable, requiring numerical approaches that no current supercomputer can fully handle. This isn't a problem that gets solved in a few years. Scientists are essentially staring at the possibility that the simplest and most powerful tool in their cosmological toolkit, the cosmological principle, is an approximation that breaks down at the scales where the universe's deepest secrets live. And the further astronomers push into those scales, the stranger the universe gets. Some of what they're finding doesn't just challenge current models. It suggests that something about the universe's deepest history may have been different from anything we currently imagine. One of the most radical proposals isn't about what the universe looks like now. It's about what happened before it began. To fully understand why the Hercules Corona Borealis Great Wall discovery was credible enough to be taken seriously, you need to understand the tool that found it. Gamma-ray bursts aren't just spectacular explosions. They're cosmic lighthouses, and scientists have learned to use them in a way that makes other mapping methods look short-sighted. Most large-scale surveys of the universe map the distribution of galaxies. You point a telescope at a region of sky, count the galaxies you can see, record their distances, and build a three-dimensional map. This works well at moderate distances, but it has a ceiling. The farther away a galaxy is, the fainter it appears. At extreme distances, ordinary galaxies become too dim to detect reliably, even with the most powerful telescopes available. Gamma-ray bursts have no such ceiling. A single burst, lasting seconds to minutes, can be brighter than 1 billion galaxies combined. Satellites detect them across the entire sky continuously, and they can be observed at distances so extreme that they're coming from times when the universe was only a fraction of its current age. They are, in practical terms, the deepest traces of cosmic structure that astronomers currently have access to. Using gamma-ray bursts as structure tracers requires a clever workaround. The bursts themselves don't represent permanent features of space. They're transient events, but their locations do represent the galaxies where they occurred, and those galaxies do trace the underlying matter distribution. By plotting where gamma-ray bursts happened across the sky, at what distances and in what concentrations, scientists can infer where large concentrations of galaxies cluster together. The team that discovered the Hercules Corona Borealis Great Wall used a catalogue of several hundred gamma-ray bursts with measured redshifts, meaning their distances were known. Redshift is the stretching of light wavelengths caused by the expansion of the universe. A higher redshift means a greater distance. By sorting the bursts by redshift and plotting their sky positions, the team built a map of burst locations across a range of cosmic distances. The clustering they found in the Hercules Corona Borealis region wasn't subtle. The statistical excess of bursts in that region, compared to random expectation, was clear enough to survive multiple independent tests. Other teams later reanalyzed the data with different software, different statistical frameworks, and larger updated catalogues. The signal remained. The limitation, and scientists are honest about this, is that gamma-ray burst catalogues are still relatively small compared to galaxy surveys. A few hundred measured bursts covering the whole sky, divided across billions of light years, creates a sparse map. Sparse maps can produce clustering signals that look real but reflect sampling irregularities rather than physical structure. This is why the Hercules Corona Borealis Great Wall carries the label of a candidate structure rather than a fully confirmed one. Confirmation will require either a much larger catalogue of gamma-ray bursts with precise distance measurements or an independent detection of the structure through a completely different type of cosmic tracer. The James Webb Space Telescope, along with other next-generation instruments coming online in the late 2020s and early 2030s, may provide exactly that. Their sensitivity at extreme distances could allow galaxy surveys deep enough to either confirm the structure directly or set firm limits on its existence. Either outcome is scientifically significant. Confirmation would force an immediate revision of the standard cosmological model at the deepest level. A non-detection would tell scientists that the gamma-ray burst method has systematic biases they need to understand and correct. Science wins either way, but many researchers suspect what the deeper surveys are going to find. And what they expect to find connects directly to a much older mystery, one that has nothing to do with the Hercules Corona Borealis Great Wall specifically, but everything to do with why the universe's largest structures keep defying expectation. 13.8 billion years. That number carries enormous weight in cosmology. Scientists arrived at it through multiple independent methods: the temperature and pattern of the cosmic microwave background, the observed expansion rate of the universe, the ages of the oldest known stars. The measurements converge. The universe is 13.8 billion years old, give or take a small margin. That number is the universe's entire lifetime. Every star that ever formed, every galaxy that ever assembled, every structure in the cosmic web grew inside that window. And 13.8 billion years, while vast by human standards, is a genuinely tight budget for building what we see in the sky. To appreciate why, consider how structure forms. The first stars ignited roughly 200 million years after the Big Bang. The first galaxies assembled over the following hundreds of millions of years. Galaxy clusters, groups of hundreds to thousands of galaxies, took longer still. The large-scale filaments of the cosmic web, the threads and walls connecting clusters across hundreds of millions of light years, required several billion years to develop into their current form. This timeline gives us a rough rate for how quickly structure can grow, and that rate, applied honestly to the largest observed structures, produces a maximum size that sits far below 10 billion light-years. Cosmologists have a term for this. They call it the growth rate problem. Given the initial density fluctuations inferred from the cosmic microwave background, the matter content of the universe, both ordinary and dark, and the expansion history driven by dark energy, the equations of structure formation produce a universe where coherent structures max out at a scale well below what we observe in megastructures like the Hercules Corona Borealis Great Wall. One attempted solution involves pushing the initial density fluctuations to be much larger than current measurements of the cosmic microwave background suggest. If the early universe had more extreme density variations, gravity would have had bigger seeds to work with, and structure could grow faster. This approach has a problem. It conflicts with the cosmic microwave background data, which shows an initial density field but is remarkably smooth and uniform, varying by only 1 part in 100,000. Another attempted solution involves modified dark energy. Standard cosmology treats dark energy as a constant, the cosmological constant Einstein introduced. But if dark energy varied over time, perhaps being stronger in the early universe, it could have altered the expansion rate in ways that allowed structure to grow faster during critical periods. Some recent data from large sky surveys does hint that dark energy may not be perfectly constant. The evidence is preliminary, but if it holds up, it changes the timeline for everything. A third proposed solution is more radical. What if the universe is older than we think? Several cosmological models have proposed mechanisms by which the universe could have an effective age longer than 13.8 billion years, either through cyclic models where the current universe emerged from a previous one, or through pre-Big Bang states where structure existed before the bang itself. These ideas are deeply speculative. They make predictions that are currently very difficult to test, but they aren't dismissed as crank science. Several serious physicists have developed them rigorously, and the growing list of overlarge structures is exactly the kind of observational pressure that pushes scientists toward exploring ideas they might otherwise set aside. The universe's age is a wall, and somehow the structures we're finding appear to have been built beyond it. Zoom out far enough from Earth, and the universe reveals a pattern that no one expected to find. Galaxies don't scatter randomly. They arrange themselves along vast filaments of matter, thin threads stretching hundreds of millions of light years, connecting dense clusters at their intersections like nodes in a net. Between the filaments lie enormous empty regions, voids where almost nothing exists. The overall structure looks strikingly like a three-dimensional foam, or like the neural network of a brain viewed from a great distance. This is the cosmic web, and it's one of the most stunning confirmations of theoretical cosmology's predictive power. Simulations run in the 1980s and 90s, using early dark matter models and basic gravitational physics, predicted the web's existence before it was directly observed. When surveys finally mapped it in detail, the match between prediction and observation was extraordinary. The cosmic web forms through the same gravitational processes described earlier. Dark matter halos pull in ordinary matter. Matter clusters along filaments. Filaments drain mass toward their endpoints where clusters grow. Over billions of years, the web becomes more sharply defined, its filaments thinner, and its voids emptier as matter continues migrating toward the densest regions. The web has a hierarchy. The thinnest threads are small filaments connecting galaxy groups. Largest filaments connect major clusters. The largest filaments, called superclusters or supercluster complexes, span hundreds of millions to low billions of light years and represent the web's primary structural bones. The Laniakea supercluster, the structure our Milky Way belongs to, stretches roughly 500 million light-years across and contains the mass of 100 million billion suns. Discovered in 2014, it was a landmark achievement in mapping our cosmic neighborhood. It was also, the researchers noted at the time, right at the upper edge of what the cosmological principle comfortably allows. Structures significantly beyond Laniakea in size start accumulating the anomalous character we've been discussing. The Sloan Great Wall, the South Pole Wall, the huge large quasar group, the giant arc, the Big Ring, the Hercules Corona Borealis Great Wall. Each one sits progressively further from what standard cosmic web formation predicts. The cosmic web's largest features may be telling us that the web itself has no true upper scale. Some researchers have proposed that the web continues to larger and larger structures with no smoothing threshold, a property called scale-free or fractal structure. A fractal universe has no characteristic scale. Zoom out at any level and you see more structure, more variation, more filaments and voids, with no scale at which everything averages out. This is in direct opposition to the cosmological principle. A fractal universe and a homogeneous universe are mutually exclusive descriptions. You can't have both. The fractal hypothesis has been around for decades, proposed by Italian physicist Luciano Pietranero in the 1980s. For years it was considered a minority position. Mainstream cosmology resisted it because the largest surveys seemed to show smoothness at very large scales. But each new survey has pushed the scale at which smoothness appears further and further away. Some researchers now argue it may recede indefinitely as our observational reach improves. If the universe is fractal all the way up, every model built on large-scale homogeneity needs rebuilding. Every calculation that assumed the universe averages out becomes an approximation that breaks at some scale, and that scale may be far smaller than we've been assuming. The fractal possibility changes everything, but there's an even stranger idea lurking behind it. One that asks whether these structures might be shadows of something that existed before the universe itself. While cosmologists wrestled with the existence of impossibly large structures, astronomers using the James Webb Space Telescope were running into a related problem from the other direction. The telescope launched in late 2021 and began delivering science images in 2022. Within its first year of observations, it had generated a quiet crisis in galaxy formation theory. The standard model predicted that the early universe would look sparse. The first few 100 million years after the Big Bang should have been dominated by small, irregular, relatively dim proto-galaxies, the raw material that would eventually merge and grow into the massive galaxies we see nearby. Large, well-structured galaxies were expected to appear only after billions of years of accumulation. What the James Webb Space Telescope found was different, at extreme distances, corresponding to times when the universe was only 300 to 500 million years old. The telescope detected galaxies that were already massive. Some contained billions to tens of billions of solar masses of stars, organized into surprisingly regular structures. One object, nicknamed the Firefly Sparkle, showed a complexity of structure at that early epoch that theorists hadn't predicted. Others were even more extreme. A team analyzing a subset of early James Webb data described finding several galaxies so massive at such early times that they exceeded the maximum mass allowed by standard models of galaxy formation by factors of 10, 100. The team's paper carried a phrase that circulated widely in physics discussions. The universe had too many massive galaxies too early. This finding connects directly to the megastructure problem. If galaxies themselves were forming faster and more efficiently than the Standard Model predicts, then the underlying matter distribution was also clumping faster than expected. Structures grow from the same seeds that form galaxies. If those seeds were more powerful, more efficient, or operating under conditions the Standard Model doesn't capture, then both the early galaxy overcrowding problem and the megastructure scale problem could share the same root cause. One candidate explanation is that the initial conditions of the universe were different from what the cosmic microwave background implies. The cosmic microwave background records the state of the universe at 380,000 years after the Big Bang. It shows a nearly smooth density field with tiny fluctuations. But those fluctuations, as seen in the background radiation, may not tell the whole story if some density variations were on scales too small or too specific to leave a clear imprint in the background's pattern. Another candidate involves the properties of dark matter itself. Standard dark matter models assume the dark matter particle, whatever it is, moves slowly, which is why it's called cold dark matter. Cold dark matter forms halos efficiently and helps galaxies assemble quickly. But the Standard Model's predictions for early galaxy masses still fall short of what James Webb is finding. Some researchers have proposed that early universe dark matter behaved differently, either in how it clustered or in whether it decayed or transformed over time. A third possibility is one that feels least comfortable to say out loud in scientific circles. The Standard Model may be missing a fundamental piece of physics that operated in the early universe and left behind both the early massive galaxies and the anomalously large structures we see at lower redshifts. The James Webb Space Telescope was supposed to confirm the Standard Model's predictions at extreme distances. Instead, with every semester of new data, it keeps finding things that require explanation. The early universe is more crowded, more structured, and more complex than anyone predicted. And the deeper we look, the more it seems the universe was building something we still don't fully understand. Two different ways of measuring the universe's expansion rate. Two different answers. A disagreement, precise enough and persistent enough, but cosmologists have stopped calling it a minor discrepancy and started calling it a crisis. The Hubble constant measures how fast the universe is expanding. Specifically, it tells you how quickly galaxies are moving away from each other per unit of distance. For every 3.2 million light-years of distance between 2 points in space, the expansion adds a certain number of miles per second to their separation. The exact value of that number is the Hubble constant. Measuring it accurately is one of the most important tasks in cosmology because the Hubble constant feeds directly into calculations of the universe's age, its geometry, the nature of dark energy, and the ultimate fate of everything. Scientists measure the Hubble constant two ways. The first method uses the cosmic microwave background, the faint afterglow of the Big Bang. By studying the precise pattern of temperature variations in this ancient light, physicists can extract the expansion rate at the time of the early universe and project it forward to the present. This method gives a value of roughly 67 kilometers per second per megaparsec. The second method measures the expansion rate directly in the nearby universe, using standard candles, objects with known brightness, primarily a type of exploding star called a Type 1 supernova. By comparing how bright these explosions appear versus how bright they should be, astronomers calculate their distances and derive the current expansion rate. This method consistently returns a value around 73 kilometers per second per megaparsec. The gap between those two numbers might sound small. It isn't. Both measurements have been refined over years by independent teams using different instruments and different calibration methods. The gap hasn't closed. If anything, it's sharpened. The two measurements are now precise enough that their disagreement is statistically significant at a level that rules out pure measurement error. Something physical is causing the discrepancy, and several leading explanations connect directly to the large-scale structure problem. One prominent hypothesis: we live inside a region of space slightly less dense than the cosmic average. This local void would cause galaxies around us to expand outward slightly faster than the global average, inflating our local measurement of the Hubble constant. The early universe measurement would correctly capture the true global expansion rate, while our local measurement would reflect our skewed position inside an unusual region. If this explanation is correct, it means the large-scale structure of the universe is inhomogeneous enough that our position within it affects our fundamental measurements of physics. The cosmological principle, which requires any observer anywhere to measure the same large-scale properties, would be violated by the simple fact that we live somewhere specific within an uneven universe. A second hypothesis involves dark energy that changes over time. If dark energy was stronger in the early universe than it is today, the universe's expansion history would differ from the standard constant dark energy model, potentially reconciling the two Hubble measurements. Both hypotheses require the standard model to be incomplete in some way. Both point toward a universe that is less uniform and less simple than the cosmological principle describes. The Hubble tension alone would be a serious problem. Combined with the megastructure discoveries, the early galaxy overcrowding from James Webb, and the large-scale anisotropy findings, it becomes part of a pattern. Multiple independent observations, using different methods, different scales, and different phenomena, are all pointing toward the same uncomfortable conclusion. The universe has more structure, more unevenness, and more complexity than our best current model accounts for. The model needs updating. The question scientists are now seriously asking is whether a modest update will be enough, or whether something far more fundamental needs to change. Gravity is the oldest force in physics. Isaac Newton described it in the 17th century. Albert Einstein rewrote the description in the 20th, showing that gravity is the curvature of space-time caused by mass. For more than a century, general relativity has passed every experimental test ever devised. It predicted black holes before anyone confirmed they existed. It predicted gravitational waves before any instrument was sensitive enough to detect them. It describes the expansion of the universe with stunning precision. And yet, when applied at the very largest cosmic scales, it may be producing results that don't match what we see. Modified gravity theories propose that Einstein's equations, while accurate at stellar and galactic scales, require corrections at the scale of galaxy clusters, superclusters, and cosmic filaments. The idea is that gravity's behavior changes at extremely low accelerations or at extremely large distances, deviating subtly but meaningfully from general relativity's predictions. The most developed modified gravity framework is called modified Newtonian dynamics, developed by physicist Mordechai Milgrom in the 1980s. Originally proposed as an alternative to dark matter for explaining galaxy rotation curves, it has since been extended into a relativistic theory. In its extended form, it predicts different rates of structure growth at large scales, compared to general relativity combined with dark matter. Some researchers have argued that modified gravity frameworks naturally produce faster structure growth at large scales, potentially explaining how megastructures like those we've discussed could assemble more quickly than the standard model allows. The math works in certain scenarios. The problem is that other observations, particularly the details of the cosmic microwave background and the behavior of galaxy clusters, constrain modified gravity heavily, making it explain the megastructures without breaking its predictions elsewhere is genuinely difficult. A newer family of theories goes further. Researchers working on scalar tensor theories of gravity propose that an additional field exists alongside the standard gravitational field, one that modifies how gravity behaves in different environments. In regions of very low density, such as cosmic voids, gravity could behave differently than in dense regions like galaxy clusters. This environment-dependent gravity could, in principle, produce different growth rates in different parts of the universe, potentially explaining both the megastructures and the large-scale anisotropy seen in surveys. These theories make very specific predictions that upcoming surveys can test. The Rubin Observatory, set to begin full operations in the mid-2020s, will map billions of galaxies across the sky with unprecedented precision. Its measurements of weak gravitational lensing, the slight bending of distant galaxy images by intervening matter, will reveal how gravity actually behaves at the scales where the standard model is struggling. If the lensing signal matches general relativity perfectly at all scales, modified gravity loses its footing. If the signal shows deviations at the largest scales, the case for new gravitational physics becomes extremely strong. Either outcome will be decisive. Scientists are building toward a window in the next decade where they will either confirm that general relativity holds all the way up, in which case the megastructures require a completely different explanation, or discover that gravity itself has a scale-dependent character we never suspected. The second option changes physics permanently. Every textbook equation describing the large-scale universe would need revision. Every simulation of cosmic structure formation would need to be rerun with different rules. The entire edifice of large-scale cosmology would require reconstruction on a new foundation. And even that might not be the deepest level of the problem, because some researchers have begun asking a question that makes modified gravity seem almost conservative by comparison. What if the megastructures aren't products of this universe's history at all, but echoes of something that existed before the Big Bang? The Big Bang is where most people's mental model of the universe begins. A singularity, an explosion, the start of space, time, matter, and energy. Everything that exists emerged from that single event roughly 13.8 billion years ago. Before it, by conventional cosmology's account, there was nothing. No space to occupy, no time in which anything could happen. The question what came before the Big Bang is supposed to be meaningless, like asking what's south of the South Pole. But a growing number of serious physicists no longer accept that answer. The problem driving this shift is exactly the kind of observational pressure we've been building through every chapter of this story. If the standard model can't explain how structures as large as the Hercules Corona Borealis Great Wall assembled within the universe's lifetime, one way out is to give gravity more time. And the most direct way to give gravity more time is to propose that something existed before the Big Bang, something that seeded the conditions from which these structures grew. The leading framework for this is called bouncing cosmology. The idea is that the universe doesn't begin from nothing. Instead, it contracts, compresses to an extremely dense state, and then bounces back outward in the event we call the Big Bang. The current universe is one phase in an ongoing cycle of collapse and expansion. Before our Big Bang, there was a previous universe contracting toward its own end, which triggered the expansion we were born into. This isn't fringe speculation. It has serious theoretical backing. Loop quantum cosmology, a framework attempting to merge general relativity with quantum mechanics, naturally produces a bounce rather than a singularity. When the equations of loop quantum gravity are applied to a collapsing universe, the singularity that classical general relativity predicts is replaced by a quantum bounce, a moment of extreme density that reverses into expansion. What makes this relevant to megastructures is the possibility of inheritance. If the pre-bounce universe had its own large-scale structure, its own filaments, voids, and walls built over billions or trillions of years, some imprint of that structure could survive the bounce and influence the initial conditions of our universe. The density fluctuations that seeded our cosmic web might not have originated from quantum noise in our Big Bang. They might be fossils of a previous cosmic era. Under this scenario, the extreme initial conditions required to seed structures as large as the Hercules Corona Borealis Great Wall wouldn't need to arise spontaneously within our universe's 13.8 billion years. They would arrive pre-installed, inherited from a cosmos far older than ours. The challenge is testing this. Signals from before the Big Bang would be enormously distorted by the extreme conditions of the bounce itself. Some loop quantum cosmology models predict subtle patterns in the cosmic microwave background that differ from standard inflation models. Researchers have searched for these patterns. So far, the results are ambiguous, neither clearly supporting nor ruling out the bouncing scenario. But the James Webb Space Telescope's early galaxy findings are adding indirect pressure. If galaxies were building themselves faster than the standard model allows, even in the early universe, one natural explanation is that the initial conditions were far from the smooth, quiet state inflation predicts. Inherited structure from a pre-bounce universe would provide exactly the kind of head start needed. The universe we inhabit may be younger than 13.8 billion years in calendar time, but cosmologically older than anything our models currently account for. And if that's true, the structures we've been studying aren't anomalies, they're memories. In the cosmic microwave background, the faint radiation left over from the Big Bang, the temperature is almost perfectly uniform across the entire sky. Almost. There are tiny fluctuations, variations of 1 part in 100,000, and those fluctuations carry encoded information about the early universe's density structure. Scientists have mapped them in exquisite detail using the Wilkinson Microwave Anisotropy Probe and the Planck satellite. Most of those fluctuations are small, scattered, statistically consistent with the predictions of standard inflation. But one feature stands out with uncomfortable clarity. In the southern sky, in the direction of the constellation Eridanus, there is a region dramatically colder than anything inflation predicts. Spanning roughly 1 billion light-years across in the sky, it's called the cold spot. The cold spot is real. Multiple independent analyses using different instruments have confirmed it. Its temperature is not hugely different from the surrounding background, only a fraction of a degree colder in absolute terms. But statistically, its combination of size, depth, and shape should occur by chance only about once in every 1,000 universes generated by standard inflation. It's a 1 in 1,000 anomaly sitting right there in our sky. Several explanations have been proposed. The most dramatic is the supervoid hypothesis. A supervoid is exactly what it sounds like, an enormous region of space containing far less matter than average. When photons from the cosmic microwave background travel through a region of normal density, they enter a gravitational well, gain energy as they fall in, and then lose that same energy climbing out. The net effect is zero temperature change. But in a universe with accelerating expansion, photons passing through a void behave differently. As the photon crosses the void itself expands slightly due to dark energy. The gravitational well the photon climbed into has become slightly shallower by the time the photon exits. The photon loses slightly more energy exiting than it gained entering. The result is a colder patch in the microwave background. In 2015, a team of astronomers announced evidence for a supervoid in exactly the right direction and at exactly the right distance to produce the cold spot through this mechanism. The void they identified spans roughly 1.8 billion light-years across, making it one of the largest known voids in the observable universe. They described it as the largest individual structure ever identified. The match between the supervoid's position, size, and the cold spot's location is compelling. Some researchers consider it the best explanation on the table. Others argue the supervoid's density contrast, how much emptier it is compared to the cosmic average, isn't quite deep enough to fully account for the cold spot's severity. The explanation fits but doesn't fit perfectly. An alternative explanation is more exotic. Some physicists have proposed that the cold spot is an imprint of a collision between our universe and a neighboring universe in a multiverse. If our universe is one bubble among many in an eternal inflationary sea, bubble collisions would leave circular bruises in the cosmic microwave background. The cold spot's roughly circular shape and its anomalous temperature profile match some predictions of bubble collision models. Bubble collision cosmology is speculative. Confirmed evidence for a multiverse doesn't exist. But the cold spot is real. It's large, and its presence in the same cosmic inventory as the megastructures and the large-scale anisotropy makes the universe's map look less and less like the simple, smooth expanse the standard model describes. The universe keeps showing us features that exceed the expected, and each one points toward the same unsettling conclusion. The map we've been drawing for decades may be missing entire dimensions of reality. What if the cosmic web has no ceiling? What if you zoom out to any scale, any distance, any volume of space, and you always find more structure, more variation? What if the universe is never actually smooth, no matter how far out you look? This is the fractal hypothesis, and it has refused to die despite decades of effort by mainstream cosmology to rule it out. A fractal is a geometric structure that repeats its pattern at every scale. Zoom in, and you see complexity. Zoom out, and you see more complexity. The level of irregularity never averages away. Coastlines are roughly fractal. River networks are roughly fractal. Neural networks in the brain show fractal properties. Nature uses fractal geometry frequently because it's an efficient result of simple iterative processes. Luciano Pietranero, an Italian physicist, formally proposed the fractal universe model in the 1980s after analyzing available galaxy distribution data and finding that the clustering statistics matched a fractal pattern rather than a homogeneous one. His claim was direct. The universe does not become smooth at any scale accessible to observation, and the cosmological principle is an idealization that doesn't match reality. Mainstream cosmology pushed back hard. The Sloan Digital Sky Survey in the 2000s seemed, at moderate scales, to show evidence for a transition to homogeneity, a scale above which the distribution of galaxies became statistically uniform. For a time, this was presented as a confirmation of the cosmological principle and a refutation of the fractal model. But the apparent transition to homogeneity kept moving. Each new survey, reaching deeper and covering a wider area, found the transition occurring at a larger scale than the previous survey had measured. And the largest structures, including those we've spent this entire journey exploring, exist at scales where the supposed transition was supposed to have already occurred. Some researchers now argue the transition to homogeneity is like a mirage. Approach it with a shallower survey and it appears to be just ahead. Reach it with a deeper survey and it retreats further. The universe keeps revealing more structure at the frontier of each new observation. The fractal interpretation has a mathematical backbone. The two-point correlation function, a statistical tool measuring how strongly galaxies cluster at different separation distances, follows a power law relationship across a remarkable range of scales. Power law statistics are the mathematical signature of fractal structure. They indicate a system with no characteristic scale, no preferred distance at which clustering suddenly stops. If the universe is genuinely fractal at all scales, the implications are staggering. Every calculation of cosmic density averages, every model of large-scale expansion, every estimate of the universe's total matter content based on assuming uniformity becomes an approximation of uncertain accuracy. The universe's mass budget, which already has dark matter and dark energy as unexplained components, would require fundamental revision. The fractal model also changes how we interpret our own position. In a homogeneous universe, every region is statistically equivalent. In a fractal universe, there's no such equivalence. Some regions are vastly denser, others vastly emptier, and the average is a statistical fiction rather than a description of any real location. We might be living in an unusually empty bubble, a relatively sparse region inside a fractal web that at larger scales continues to build structure we haven't yet mapped. Or we might be in an unusually dense filament. The fractal hypothesis doesn't privilege any position, including ours. The next generation of sky surveys will push the homogeneity question to much larger scales with much higher statistical confidence. Within 10 years, we will either find the transition to homogeneity at a definitive scale, or find that it continues to retreat. One of those outcomes saves the cosmological principle, the other may end it. When the Big Bang happened, the universe went through a rapid transition from an unimaginably hot, unified state to the cooler, differentiated state we inhabit today. As it cooled, the forces of nature separated from each other in a process physicists compare to water freezing into ice. When water freezes quickly and unevenly, cracks form. The ice doesn't become one perfect crystal. It becomes a lattice of crystals with boundaries and defects between them. The universe may have done the same thing. Those defects are called topological defects. Depending on their geometry, they can take the form of points, one-dimensional lines, or two-dimensional sheets. The one-dimensional version, stretched across cosmic scales, is what physicists call a cosmic string. A cosmic string is a hypothetical crack in the fabric of space-time. It carries no width in the conventional sense. It is essentially a one-dimensional line of concentrated energy, so dense that a single inch of cosmic string would outweigh an entire mountain range. It curves space-time around it, dramatically. Objects passing near a cosmic string experience its gravitational influence without the string having any surface to interact with. Cosmic strings are a prediction of certain unified field theories, models that attempt to describe all four forces of nature within a single mathematical framework. Their existence hasn't been confirmed. Despite searches in the cosmic microwave background, in gravitational wave signals, and in galaxy distribution data, no definitive detection of a cosmic string has been announced. But here is why the Big Ring and the giant arc have revived interest in them. A cosmic string stretched across billions of light-years of space would leave an imprint on the surrounding matter distribution. Galaxies would cluster along the string's path, pulled by its intense gravitational field. From a distance, that clustering would look exactly like a long, curved arc of galaxies. A closed loop of cosmic string, a ring of concentrated space-time curvature, would produce a circular imprint. Galaxies would cluster around its perimeter, tracing its shape. From far away, that imprint would look exactly like the Big Ring. The geometric precision of the Big Ring is one of its most striking features. Natural gravitational collapse produces filaments and walls with irregular, organic shapes. The ring is too symmetrical for standard gravitational collapse to explain comfortably. Cosmic strings, being geometric by nature, would produce more regular structures. Alexia Lopez, who discovered both the giant arc and the Big Ring, has publicly stated that cosmic strings are among the explanations her team is actively considering. The proximity of the two structures in the sky, separated by only 2 degrees, and their similar distances from Earth raise the possibility that they are two different sections of the same underlying cosmic string network, seen at different orientations. The implications of confirmed cosmic string detection would be enormous. It would provide direct evidence for physics beyond the standard model of particle physics. It would confirm that the early universe underwent phase transitions energetic enough to create one-dimensional topological defects. And it would give structure formation a new mechanism, one that operates at all cosmic scales and doesn't need billions of years of gradual gravitational accumulation to produce geometric megastructures. Cosmic strings could build large structures fast, precisely the kind of fast that the universe seems to require. The search is active. Upcoming gravitational wave detectors, including the Laser Interferometer space antenna planned for launch in the early 2030s, should be sensitive enough to detect the gravitational wave background produced by a network of oscillating cosmic strings, if it exists. If the signal appears, it will answer one of the biggest questions in cosmology, and it will raise an even bigger one about what else the Big Bang left behind. The Hercules Corona Borealis Great Wall challenges cosmology from one direction: too much matter, too organized, across too vast a distance. But the universe's assault on the Standard Model comes from the opposite direction too. Enormous voids, regions of almost total emptiness stretching billions of light years, are also pushing the boundaries of what the models say should exist. The KBC void is one of the most consequential. Identified formally in 2013 and named after the astronomers Keenan Barger and Cowie, it is an enormous underdense region of space that may contain our entire local group of galaxies near its edge. The void spans roughly 2 billion light-years across, making it one of the largest known void structures in the observable universe. What makes the KBC void directly relevant to the Hubble tension is its potential effect on our measurements. If our galaxy, our cluster, and our immediate cosmic neighborhood sit inside a region significantly less dense than the universal average, then the galaxies we use to measure the local expansion rate are all inside an unusual bubble. Expansion inside a void runs slightly faster than the global average, the way water flows quicker where a riverbed narrows. If we're measuring the Hubble constant from inside a void, our local measurements would consistently come out higher than the true global value. The discrepancy between the early universe measurement and the local measurement, the Hubble tension, could be partly or entirely a consequence of our unusual address in the cosmic web. Studies attempting to measure the KBC void's depth, how much less matter it contains relative to average, have produced varying results. Some analyses suggest it's deep enough to account for a significant fraction of the Hubble tension. Others suggest it falls short. The precise density profile of the void is genuinely difficult to measure because we are inside it, and measuring the density of a structure from within it is like trying to judge the size of a room by looking at one wall. What's unambiguous is that the KBC void exists. It's enormous, and its existence at that scale is another challenge for the Standard Model. Voids this large, like structures this large, require explanation. Standard cosmology produces voids as the natural inverse of filaments. Matter drains out of voids toward filaments over time. The largest voids in standard simulations reach several 100 million to about 1 billion light-years across. 2 billion is again above the expected ceiling. The symmetry here is worth appreciating. The universe's anomalies appear both in its densest regions and its emptiest ones. It's overbuilt where it should be smooth, and hollowed out where it should be moderately filled. The Standard Model's predictions are being violated from both directions simultaneously. Some researchers have proposed that the KBC void and the large-scale structures like the Hercules Corona Borealis Great Wall are connected parts of a single large-scale pattern. A cosmic topology where enormous walls bound enormous voids in a cycle of density contrast that plays out across scales the Standard Model was never designed to describe. If that's correct, the universe at the very largest scales isn't organized like the cosmic web's filaments and sheets. It's organized like something different, something we don't have a complete model for yet. And the clues for what that model might look like are encoded in a faint glow that fills the entire sky, a relic signal from the universe's infancy that scientists have only recently begun to read at the depth it deserves. The cosmic microwave background is the universe's oldest photograph, taken 380,000 years after the Big Bang. It captures the moment the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. That light has been traveling ever since, stretched by cosmic expansion from visible light into microwave radiation, and it reaches us from every direction in the sky with almost perfect uniformity. Scientists have treated it as the Rosetta Stone of cosmology, The pattern of tiny temperature variations encoded in it, 1 part in 100,000 from place to place, carries information about the density fluctuations that seeded all subsequent structure. Read those fluctuations correctly, and you can infer the universe's composition, its geometry, its expansion history, and its eventual fate. The Planck satellite, which mapped the cosmic microwave background in unprecedented detail and published its final results in 2018, confirmed the standard cosmological model with remarkable precision. The composition of the universe, the properties of dark matter and dark energy, the geometry of space, all came out consistent with theory. It was a triumph. And yet, within that triumph, several anomalies persisted that the Planck team acknowledged without fully resolving. The cold spot we already discussed. But there were others. The hemispherical power asymmetry. One half of the sky has slightly stronger temperature fluctuations than the other half. The standard model predicts the two halves should be statistically identical. They aren't. The alignment of the lowest multipoles, the largest scale patterns in the cosmic microwave background, show a surprising alignment with the plane of the solar system and the direction of the cosmic equinox. This alignment makes no sense in a universe that has no preferred directions. It could be a systematic measurement artifact. Several careful studies have suggested it's real. Each of these anomalies is individually explainable as a statistical fluctuation. The universe is big, and rare events happen somewhere. One anomaly in one map doesn't overturn a model, but the accumulation of anomalies in the same map, all pointing toward large-scale asymmetry or preferred directionality, forms a pattern that some cosmologists find increasingly hard to attribute purely to chance. If the large-scale anisotropy seen in galaxy surveys, quasar alignments, bulk galaxy flows, and the cosmic microwave background anomalies are all manifestations of the same underlying feature, then the universe has a preferred structure at enormous scales that predates the formation of any galaxy or filament, a structure built into the initial conditions themselves. That structure would have to have been set before or during the inflationary epoch, the first fraction of a second after the Big Bang. Standard inflation erases large-scale structure through its rapid expansion, smoothing out any pre-existing asymmetries. If the asymmetries survived inflation, either inflation was unusual, or the pre-inflationary universe had an extremely powerful asymmetry that inflation couldn't fully smooth away. This ties directly back to the pre-Big Bang hypothesis. An asymmetric, bounced universe could imprint preferred directions on the initial conditions. A universe born from an anisotropic collapse would emerge with a directional preference built in, subtle enough to survive inflation, but persistent enough to show up in the cosmic microwave background and in the distribution of the largest structures. We may be living in a universe that remembers its own birth, and that birth was far more complex than a simple uniform explosion. Everything we can see, every galaxy, every structure, every signal that has ever reached our telescopes exists within a sphere roughly 93 billion light-years across, the observable universe. This boundary isn't a wall. It's a horizon, defined by the age of the universe and the speed of light. Beyond it, space continues. The universe extends further than any signal can reach us in our lifetime or in the lifetime of our civilization. How much further is genuinely unknown. Cosmological models allow for several possibilities. The simplest is that the universe is infinite, extending without boundary in every direction. Infinite space filled with matter would produce an infinite number of galaxies, an infinite cosmic web, and an infinite variety of structures. In an infinite universe, every possible configuration of matter exists somewhere. Every arrangement, every structure, every pattern repeats infinitely. The observable universe is just one patch in an endless sea. An infinite universe makes the Hercules Corona Borealis Great Wall less surprising but more conceptually overwhelming. If space is infinite, structures larger than anything we can observe are guaranteed to exist somewhere beyond our horizon. The wall we found at 10 billion light-years might be modest compared to what lies beyond. A finite but unbounded universe is also possible. Imagine the surface of a sphere. You can travel across it in any direction without hitting a boundary, but the total area is finite. The universe might have a similar topology in 3 dimensions, meaning it wraps around itself at some scale larger than the observable universe. In this case, the total volume of the universe is large but not infinite, and the largest possible coherent structures are limited by the total size of space. Some models of eternal inflation propose a multiverse, a vast collection of bubble universes, each experiencing their own Big Bang and their own physical constants. Our observable universe is one bubble. The others are forever beyond our horizon, unreachable and undetectable. The megastructures we see inside our bubble are features of our particular cosmic history, but other bubbles might have entirely different large-scale structures, or none at all. What's humbling about this is the epistemic problem it creates. Every piece of evidence we've discussed, every megastructure, every anomaly in the microwave background, every tension in the Hubble constant, comes exclusively from within our observable horizon. We have no data from beyond it. We are reasoning about the nature of the entire universe from one small patch, the way you might try to infer the shape of a continent by staring at 1 square mile of ground. Our patch might be typical, or it might be unusual. We can't know, and the scientific method as currently practiced can't tell us. The cosmological principle was partly an assumption of typicality, a hope that our observable region is representative of the whole. The anomalies we're finding suggest our region might have features that aren't universal. The universe beyond our horizon isn't science fiction. It's a physical reality that exists and is affecting the cosmos we inhabit right now, through gravitational effects that flow across the boundary we can never cross. We can't see the source, but we may be feeling its influence in the very structures that defy our models. The largest structures in our observable universe might be, by comparison to what lies beyond, the smallest features of a pattern too vast for any civilization to ever fully map. This chapter is territory that most physicists approach cautiously. The simulation hypothesis sits at the boundary between serious physics and philosophy, and most scientists prefer to stay on the physics side. But the existence of megastructures that defy explanation has a way of forcing even careful thinkers to ask questions they'd normally avoid. The simulation hypothesis proposes that the universe we inhabit is a computational process running inside a more advanced system. The physical laws we observe are the rules of the simulation. The constants of nature are parameters. The universe's history is an execution of a program, with initial conditions set by whoever designed the computation. The idea gained unexpected academic traction in 2003 when philosopher Nick Bostrom published a rigorous probabilistic argument suggesting that if any civilization ever achieves the ability to run high-fidelity simulations of conscious beings, and if such civilizations run many such simulations, then statistically, the vast majority of conscious beings in existence would be simulated rather than biological. Bostrom's argument is logical, not scientific, meaning it doesn't produce testable predictions in the usual sense. But some physicists have asked what signatures a simulated universe might leave in its physics, and some of those signatures sound uncomfortably familiar. One predicted signature involves the computational cost of detail. A simulation would likely allocate rendering resources based on what the simulation's inhabitants can actually observe. Deep space regions, never directly visited and only observed from extreme distance, might be rendered with lower resolution. The statistical properties of those regions could differ subtly from those of well-observed nearby regions. The anomalies in the cosmic microwave background particularly the alignments and the hemispherical asymmetry, could be interpreted as low-resolution rendering artifacts. The cold spot could be an underdeveloped patch in a simulation focused on higher detail local physics. The megastructures, existing at scales no civilization has ever physically explored, might reflect different computational rules applied at extreme distances. This is speculation of the highest order. There is no confirmed physics mechanism that would produce these specific anomalies in a simulation. The interpretation is post hoc, fitting the hypothesis to the data rather than predicting the data from the hypothesis. But here is why serious physicists mention it at all. The anomalies we've discussed are not obviously explainable by any other current framework either. The simulation hypothesis is wrong for the same reason most physical theories are provisionally wrong. We lack evidence. But it is at least coherent. It describes a universe where anomalies at large scales are expected features, not surprises. More grounded is the related observation that the universe's physical constants appear fine-tuned to allow the existence of complex structures and eventually life. Alter the strength of gravity, the mass of the electron, or the cosmological constant by small amounts, and the universe becomes sterile, either collapsing immediately or expanding too fast for stars to form. The fine-tuning problem is a genuine unsolved question in physics. Megastructures don't resolve the fine-tuning problem, but they do reinforce the strangeness of the universe's apparent design at every scale, from the precise value of the cosmological constant allowing expansion to continue at just the right rate, to structures so large they shouldn't exist within the universe's lifetime. The cosmos appears to operate with properties at its extremes that our theories, built from observations of middle scales, struggle to predict. Whether that strangeness points towards simulation, multiverse selection, new physics, or simply the limits of current models, is a question the evidence hasn't yet resolved. But the next generation of telescopes will push into the scales where the evidence either starts to clarify or deepens the mystery further, and what they find may settle debates that have persisted since the first anomalies appeared. The next decade in astronomy may be the most consequential since Galileo pointed a crude lens at the sky. A collection of observational instruments, each more powerful than anything previously built, is either already operational or approaching completion. Together, they will push our map of the universe to scales and depths that make current surveys look like rough sketches. The Vera C. Rubin Observatory in Chile represents one of the most ambitious sky surveys ever attempted. Its telescope will scan the entire southern sky repeatedly over 10 years, building a catalogue of billions of galaxies with measured distances, shapes, and brightness histories. This survey will map the large-scale structure of the universe out to several billion light-years with a statistical completeness that dwarfs anything previously achieved. The structures we've been discussing, including the giant arc, the big ring, and their cosmic neighbors, will be placed in context by a map so detailed that their status as genuine coherent structures or statistical artifacts will become definitively clear. The Rubin Observatory's weak lensing measurements will also test how gravity behaves across the scales where megastructures exist. If gravity is modified at large scales in the ways some theorists propose, the lensing signal will show it. The Euclid Space Telescope, launched in 2023 and beginning its science operations, will map 3 dimensions of the universe over 1/3 of the entire sky, charting the positions of billions of galaxies out to 10 billion light-years. Euclid's primary scientific goals include measuring the Hubble constant, probing the nature of dark energy, and testing the cosmological principle through the most precise galaxy clustering measurements ever made. Its data will directly address the tensions and anomalies that currently strain the standard model. The Nancy Grace Roman Space Telescope, expected to launch in the late 2020s, will combine wide-field imaging with spectroscopy at depths comparable to the Hubble Space Telescope, but across an area roughly 100 times larger. It will detect galaxies from times when the universe was only a small fraction of its current age, providing an inventory of early structure formation that will either confirm or directly challenge the James Webb Space Telescope's finding of too many massive early galaxies. The Square Kilometre Array, a radio telescope spanning 2 continents, will survey hydrogen gas across enormous volumes of the universe, tracing the cosmic web's threads in a completely different wavelength regime. Its observations will be independent of optical galaxy surveys, providing a check on whether the structures found in galaxy catalogues are genuine features of the matter distribution or artifacts of how light behaves in optical telescopes. For the specific case of the Hercules Corona Borealis Great Wall, the key advancement will come from more complete gamma-ray burst catalogues, combined with improved redshift measurements. New space missions designed to detect and localize gamma-ray bursts with greater precision will provide denser sampling of the structure's claimed extent. If the wall is real, the denser sampling should sharpen its outline. If it was a statistical artifact of a sparse catalogue, the new data will dilute the signal. The timeline is tight but real. Within 10 to 15 years, the major observational questions surrounding the universe's largest structures will have decisive answers. Either the structures dissolve under higher resolution scrutiny, confirming that current anomalies reflect data limitations, or they solidify into undeniable features that the standard model has no path to accommodate. If they solidify, the field will face a genuine paradigm shift. Every physicist alive will have to reckon with a cosmos that behaves differently at its largest scales than our best theories predict. And that reckoning will force a question about what the universe's asymmetry and impossible structures ultimately mean for the species standing on one small planet, looking up and trying to make sense of it all. Strip away the technical vocabulary, set aside the equations and the statistical significance values, and the survey catalogues. Ask the fundamental question plainly: what does it mean if the universe is genuinely different from what we thought? It means our maps are wrong, and when your map is wrong, you can still walk, but every destination is less certain than you believed. Modern cosmology's map describes a universe born from a hot, uniform state, evolving under 4 known forces, filled with known matter and 2 unknown components, dark matter and dark energy, proceeding toward a cold, empty eventual fate. It's a map built on decades of painstaking observation and theoretical work. It has predictive power. It has been tested and refined. It is the best map we have. But maps are not territory. A map's accuracy is conditional on its underlying assumptions. The cosmological principle is one of those assumptions. If it fails, the map needs redrawing. How much redrawing depends on how badly it fails and at what scales. A modest failure, where the principle holds reasonably well except at the very largest scales, would require extensions to the standard model. New components, new mechanisms, modified equations that recover the standard model at smaller scales while producing the observed megastructures at large ones. This would be significant physics. It would probably earn a Nobel Prize or 2, but it wouldn't overturn physics at its foundations. It would expand the map's edges. A deep failure where the cosmological principle breaks down in a way that threads through multiple phenomena simultaneously. The Hubble tension, the early galaxy problem, the quasar alignments, the cold spot, the megastructures, would require something closer to a revolution. New frameworks for gravity, new physics in the early universe, potentially a complete revision of how we model cosmic expansion. This would be the kind of scientific revolution that happens once or twice per century. The philosophical weight is considerable. Every civilization that has looked at the sky has built models of the cosmos, and every generation that built those models believed, with good reason, that they were approaching a final truth. The universe, it turned out, kept revealing new layers. The The solar system was not the cosmos. The Milky Way was not the cosmos. The observable universe is probably not the complete cosmos. Each expansion of the map was also a demotion of human centrality and a humbling of human certainty. The megastructures are asking us to perform that demotion again. They are evidence that the universe at its largest scales operates according to rules we haven't fully written yet. That our 13.8 billion year old, 93 billion light-year wide observable slice of reality contains features that don't fit the framework we've built over a century of the most rigorous science our species has ever practiced. This isn't cause for despair. Science is self-correcting. The same rigor that built the standard model will extend it, revise it, or replace it. The anomalies don't invalidate everything we know. They identify where the known ends and the unknown begins. And that boundary, the edge of the map, is where science is most alive. The next generation of physicists will spend their careers at that edge, equipped with more powerful tools, broader data sets, and a growing list of phenomena demanding explanation. They will push the map further than any previous generation. Some of them haven't been born yet. Some are children right now, somewhere on this planet, who will eventually stand in control rooms watching data stream in from telescopes aimed at the universe's oldest, largest secrets. What they find will change what it means to be a conscious species in a cosmos that keeps turning out to be larger, stranger, and more structurally complex than we imagined. The Hercules Corona Borealis Great Wall exists. It is 10 billion light-years across. It should not be possible. And the universe built it anyway. Thought experiments are science's way of making the impossible feel tactile. Physicists use them to test intuitions that mathematics alone can't fully communicate. So consider this one. Place yourself, mentally, at the center of the Hercules Corona Borealis Great Wall. What would you experience? First, the darkness. Space is vast and mostly empty even inside a galactic wall. You wouldn't see a solid structure surrounding you. You would see galaxies, thousands of them, spread across your sky in every direction, their light points blurring into smears of billions of stars each. In the direction perpendicular to the wall's plane, the galaxy density would drop off. In the directions along the wall, it would stretch to the horizon of your instruments, galaxies upon galaxies receding into distance. At the center of the wall, you would be surrounded by roughly 10 billion light-years of galactic structure in the widest dimension. The nearest major galaxy cluster in any direction would likely be millions of light-years away. You would be inside the densest part of the largest known structure in the observable universe, and you would still be profoundly, incomprehensibly alone. Your sky would look noticeably different from ours. In our location, the distribution of galaxies in the distant sky is relatively even. From the center of the wall, the distant sky in the wall's plane would show a far higher density of galaxies than in directions pointing away from the wall. The cosmic web would look uneven in a way that an observer inside it could potentially measure and feel in the cosmological sense. The time dimension makes this thought experiment stranger. The light you would see from the galaxies closest to you within the wall would have left those galaxies millions of years ago. Light from galaxies on the far edge of the wall, 10 billion light-years away, would have left when the universe was barely 3 billion years old. Our solar system wouldn't form for another 5 billion years after that light began its journey. You would simultaneously be seeing the ancient past of your own wall stretched across time, like a living fossil record. An observer at the center of the wall would face an interesting cosmological challenge. Their local measurements of the universe's structure would be dominated by the wall itself. Their measurement of the Hubble constant might differ from ours, skewed by the wall's gravitational influence on surrounding matter flows. Their cosmic microwave background map might show asymmetries in different directions than ours, shaped by the enormous mass distribution surrounding them. This is a reminder that every observation we make is made from a specific location. Our measurements of the universe are taken from inside the cosmic web, inside a supercluster, inside a galaxy. From the surface of one planet, every number we extract from the sky carries the fingerprint of our position. If we were inside the wall, we might struggle even harder to identify the cosmological principles violations, because we'd be deep inside the largest known violation of it, looking outward. Or we might find the violations more obvious, because the wall's mass would be imposing its signature on every measurement we made. There are likely civilizations somewhere in that structure. If they exist, they are looking at a different sky, measuring a different Hubble constant, and potentially building a different model of the universe than the one we've spent a century constructing. The same reality, different maps, both incomplete. Of all the unknown quantities in cosmology, dark energy is the one that keeps physicists up at night most reliably. It makes up roughly 68% of everything in the universe. It drives the accelerating expansion that will eventually pull all galaxies beyond each other's observable horizons. And despite being the dominant component of the cosmos, its nature remains completely unknown. Dark energy was inferred in 1998 when two independent teams studying distant Type Ia supernovae discovered that the universe's expansion was accelerating rather than slowing. Gravity should be braking the expansion over time. Instead, the expansion was speeding up. Something was pushing outward with a strength that overwhelmed gravity at the largest scales. The simplest description of dark energy is as a cosmological constant, an inherent property of space itself. Empty space carries a fixed energy density. As the universe expands, more space exists, and therefore more dark energy. That increasing total energy drives increasing acceleration. The cosmological constant description fits current data reasonably well and is the basis of the standard lambda CDM model. The problem is the value. Quantum field theory, the framework governing particle physics, predicts that the vacuum of space should have an enormous energy density from quantum fluctuations. When physicists calculate the predicted vacuum energy density from quantum theory and compare it to the observed value of the cosmological constant, the two numbers differ by about 120 orders of magnitude. That is the largest discrepancy between theory and observation in the history of physics. This failure is so extreme that many physicists suspect the cosmological constant isn't truly constant. Perhaps dark energy is a field that evolves over time, stronger or weaker at different epochs, with the current value representing a coincidence of the moment rather than a fixed property of space. Recent data from the Dark Energy Spectroscopic Instrument, which published results in 2024 based on mapping millions of galaxies, provided preliminary evidence that dark energy's strength may have varied over cosmic history. The evidence was described as suggestive, but not definitive. If confirmed, it would represent the first direct observation of dark energy evolution, and it would require revising the standard model immediately. Dark energy's potential evolution connects directly to the megastructure problem. If dark energy was weaker in the early universe, gravity's influence on structure formation would have been stronger relative to the expansion rate during that critical early period. Stronger relative gravity, operating over longer effective timescales, could produce larger structures than the standard constant dark energy model allows. A time-varying dark energy field could, in principle, provide part of the missing mechanism for assembling the Hercules Corona Borealis Great Wall and the other anomalously large structures. It wouldn't solve the problem entirely. The timescale and causal contact constraints remain, but it would shift the ceiling of what's theoretically possible for structure growth. Dark energy also connects to the question of the universe's long-term fate. If dark energy remains constant or strengthens, the universe's accelerating expansion will eventually isolate every galaxy group in its own causally disconnected bubble. A cold, dark, quiet ending called the Big Freeze. If dark energy strengthens dramatically, space could tear apart faster than matter can hold together, ending in a big rip. If dark energy weakens or reverses, the universe could eventually recollapse in a big crunch. The megastructures we've discovered are living in a window of cosmic time where dark energy has only recently come to dominate over matter. A few billion years ago, matter's gravity was stronger than dark energy's push. The structures that formed during that matter-dominated era are the last ones of their kind. Dark energy is now winning. No new megastructures of this scale will ever form again. The ones we found are the universe's final large-scale architectural achievements. We are observing them at exactly the right moment in cosmic history. A billion years later, they will have begun to dissolve into isolated fragments as dark energy pulls their components apart. To fully grasp what the universe looks like at its largest scales, stop picturing galaxies as isolated points scattered through empty space. Picture them as the bright nodes of a three-dimensional net, a web of matter connecting everything to everything else, with enormous hollow bubbles between the threads. The cosmic web is the universe's true architecture. Filaments of dark matter and gas stretch between galaxy clusters like the strands of a spider web. At every junction where filaments cross, clusters grow dense and bright. Between the filaments, cosmic voids expand, growing emptier over time as matter continues draining outward along the web's threads. Astronomers have mapped this web in progressively finer detail over the past 3 decades, and what they've found has genuinely astonished the scientific community, not just for its structure, but for its strikingly biological appearance. Images of the cosmic web placed side by side with images of neural networks in the human brain, or the structure of mycelium networks underground, are nearly indistinguishable at first glance. The physics producing these patterns is completely different, but the mathematical structures that emerge from self-organizing systems with long-range interactions show deep similarities. This isn't mysticism, it's geometry. Networks of nodes connected by threads, with the connections governed by an inverse square law. Whether gravity in space or electrical signaling in neurons naturally converge on similar topological forms. The universe isn't conscious, but its structural logic rhymes with the logic of minds. The megastructures we've been studying, the Hercules Corona Borealis Great Wall, the Giant Arc, the Big Ring, the Sloan Great Wall, the South Pole Wall, all sit within or at the boundaries of this web. They are its largest, most extreme features. The places where the web's threads converge into structures so massive that our models predicted they shouldn't exist. Understanding the web's full extent requires mapping it at scales we've barely begun to probe. Current galaxy surveys have mapped it reliably out to a few billion light-years. The structures they reveal already challenge the cosmological principle, extending that map to 10 billion light-years and beyond, which the Euclid telescope and the Rubin Observatory will begin to do, will either show the web smoothing into featureless uniformity at large scales, or reveal an even more complex architecture than anyone currently imagines. Some cosmologists have proposed that the cosmic web extends with similar statistical properties all the way to the edge of the observable universe and beyond. Under this view, the universe is a single connected structure from its smallest gravitational threads to its largest walls and voids, a web with no true characteristic scale and no transition to homogeneity. If that's correct, the universe has been telling us something about its fundamental nature every time we've pushed our observations to a new depth. Every time we extended our maps, the web continued. Every time we expected smoothness, structure appeared. The message has been consistent. We just haven't fully accepted what it implies yet. The implication is that the universe's geometry is not the simple, uniform cosmological principle obeying space our models assume. It is a structured entity at every scale, from the filaments connecting neighboring galaxy groups to the walls enclosing billion light-year voids, all the way up to whatever lies beyond our observational horizon. That structured entity built the Hercules Corona Borealis Great Wall. It built the Big Ring. It carved out the KBC Void. And it's building and carving even now, on timescales that make human civilization feel like a momentary spark. We are part of the web, one planet, one star, one galaxy, one node among trillions. And the web is far older, far larger, and far stranger than we've managed to map. At some point in the last few centuries, something remarkable happened on the third planet of an unremarkable star in an ordinary spiral galaxy. The matter that makes up this planet became organized in a way complex enough to wonder about its own origin. Carbon, oxygen, hydrogen, nitrogen, atoms forged in stellar cores and scattered by supernovae across billions of years, assembled into nervous systems capable of asking, where did all of this come from? And how large is it? The audacity of that question is worth pausing on. A species that has existed for a few 100,000 years, on a planet only 4.5 billion years old, in a galaxy that is 12 billion years old, inside a universe nearly 14 billion years old, started pointing instruments at a wall of galaxies 10 billion light-years away and asking whether its existence breaks the laws of physics. The telescopes we built to ask that question are fragile instruments housed on a planet with an unstable climate, funded by civilizations that regularly struggle with their most basic priorities. And yet the data they produce has genuine power to falsify or confirm ideas about the nature of reality at the largest scales. Human science, for all its limitations, has proven capable of genuinely probing the structure of the cosmos. The Hercules Corona Borealis Great Wall is one of the universe's answers to our questions. Not a comforting answer, a deeply challenging one. The universe appears to have built something that it shouldn't have been able to build under the laws as we currently understand them. That challenge is a gift, in the scientific sense. Every anomaly is an invitation. Every structure that defies the model is a pointer towards something deeper. The history of science is a history of anomalies that eventually forced better theories into existence. Mercury's orbital precession didn't fit Newtonian gravity. Einstein's general relativity explained it and opened a century of new physics. The photoelectric effect didn't fit classical electrodynamics. Quantum mechanics explained it and revealed the probabilistic underpinning of reality. Every crack in a model has preceded an expansion of understanding. The cracks appearing now in the standard cosmological model, the megastructures, the Hubble tension, the early galaxy problem, the large-scale anisotropies, are numerous enough and consistent enough that they almost certainly point towards something real. Some missing component, some misunderstood mechanism, some phenomenon operating at the largest scales that our theories haven't captured yet. When that missing component is found, and eventually it will be found because someone refused to look away from the anomaly. Someone decided that a structure 10 times too large to exist was more interesting than it was inconvenient. Someone ran the statistics one more time, built the next telescope, pushed the survey one redshift bin deeper. The Hercules Corona Borealis Great Wall exists 10 billion light-years above your head in some direction right now. Its galaxies are moving, its filaments are thinning under dark energy's expansion, its stars are living and dying and scattering the elements of future planets into space. It has been there for most of the universe's existence, completely indifferent to whether anything ever found it or tried to understand it. And then we looked, and nothing has been the same since. Step back now, look at the full picture. Every chapter of this journey led to the same set of questions from a different angle, and those angles are now converging. The Hercules Corona Borealis Great Wall is too large to have formed in the universe's lifetime under current physics. The cosmological principle, which assumes large-scale uniformity, is being violated by a growing list of confirmed structures. The James Webb Space Telescope is finding galaxies too massive and too well formed in the early universe. The Hubble tension indicates that our measurements of expansion disagree with each other in a way that measurement error alone can't explain. The cosmic microwave background carries anomalies that suggest large-scale directional preference. The KBC void may be distorting our fundamental measurements of physics from inside its walls. Dark energy may not be constant. Gravity may behave differently at extreme scales. The cosmic web may have no true smoothing scale. These are separate observations made by separate teams using separate instruments and separate methodologies, and they all point toward the same conclusion. The standard model of cosmology is incomplete at its largest scales. The incompleteness might be modest, requiring extensions rather than demolition. It might be deep, requiring a new foundational framework. Scientists don't yet know which, and they're being careful not to overclaim. But the data is becoming impossible to avoid. What unites all of these threads is structure. The universe, at every scale where we've pushed our observations to their limits, contains more structure than it should. More density contrast, more coherence, more organization extending over greater distances and into greater antiquity than our models predict. Something organized this cosmos more powerfully and more extensively than 13.8 billion years of gravity operating on a smooth initial state should have managed. Whether that something is modified gravity, pre-Big Bang inheritance, cosmic strings, a time-varying dark energy, or something genuinely new, it left its fingerprints on everything we're observing. Those fingerprints are the data, and the data is the only reliable guide. The next decade will be the most observationally decisive in the history of cosmology. The instruments are ready, or nearly so. The surveys are underway. The statistical frameworks to analyze the incoming data are being built and tested. Within 10 years, the standard model will either be confirmed to hold even at the scales that currently challenge it, or it will be formally extended, revised, or in extreme cases replaced. Either outcome is a scientific achievement of the highest order. Either outcome will change our understanding of the cosmos. Either outcome will be the result of the same human impulse that made some astronomer step back from a map of gamma-ray bursts and go quiet at what the dots were saying. Science doesn't promise comfort. It promises accuracy, eventually, through iteration, failure, revision, and the relentless application of curiosity to data. The cosmos rewards that curiosity with answers. Always bigger, always stranger, always more humbling than the previous answer. That is the deal. And for everyone willing to take it, the universe still has enormous secrets left to reveal. Every generation inherits a cosmos shaped by the observations of the one before it. The astronomers who spent their lives mapping galaxy distributions in the 1980s handed the next generation a cosmic web. The teams that discovered dark energy in the late 1990s handed their successors an accelerating universe. The Planck satellite team that published its final results in 2018 handed the current generation a cosmic microwave background map of astonishing precision, along with a handful of anomalies they couldn't explain. This generation is inheriting something larger and more complicated than any previous one. A wall of galaxies 10 billion light-years across, a ring of cosmic geometry that has no clean explanation, an arc of matter bending across 3 billion light-years of sky, galaxies forming too early and too fast, an expansion rate that measures differently depending on where you look, a cold spot in the sky's oldest light, a void we might be living inside of, dark energy that might not be constant after all. Each of these is a thread, None of them has been followed to its end. The cosmologists and astrophysicists currently in graduate school will spend the better part of their careers following those threads. Some of what they find will confirm existing explanations. Some will force revisions. A small fraction of it may force a revolution, the kind that only happens a few times per century and reshapes the entire field when it does. The Hercules Corona Borealis Great Wall will remain a central exhibit in that investigation. It is the most extreme known violation of the cosmological principles predictions. Its confirmation through future gamma-ray burst surveys and eventual direct galaxy mapping at extreme redshifts will be one of the landmark moments in 21st century astronomy. If it holds up under higher resolution scrutiny, and many researchers expect it will, the conversation about what it means will become unavoidable. That conversation is already starting. It's happening in seminars and workshops and preprint servers. Physicists who were trained on the Standard Model, who built their careers within it, are asking openly whether its foundations need rethinking. The questions they're asking are careful and technical, but they translate plainly. Is the universe really as simple as we assumed? Did we build our model on a principle that doesn't hold? The honest answer, at this moment, is probably not, and probably not entirely. The universe is almost certainly more complex, more structured, and less symmetric than the model assumes. How much more is the question the data will answer? For everyone following this science from the outside, the key insight is this: anomalies are not failures. Every scientist who has ever overturned a model did it by taking an anomaly seriously rather than explaining it away. The Hercules Corona Borealis Great Wall is an anomaly that resists explanation. It demands better physics, and better physics, when it comes, will describe a universe more accurately, more completely, and inevitably more wonderfully than the description we carry. The universe built a structure that shouldn't exist. We found it. We couldn't explain it, so we built better tools, wrote better equations, and pushed further into the dark. That sequence, find, question, build, push, has driven every major advance in the history of science. It will drive the next one too. The wall is out there, 10 billion light years wide, waiting, and we are still looking.